Okay. Now, what if the velocity changes? What if the object is speeding up? How might we measure a change in velocity? Well, just like we measured a change in position, and that was the velocity, the average velocity. What if the velocity is changing? We might have some initial velocity and some final velocity. Again, we will write the final velocity as v with no subscript and the initial velocity as v naught. We'll take the change in the velocity, v minus v naught, over the change in time, t minus t naught. This is what we will describe as an acceleration. A change in velocity we'll describe as an acceleration. Imagine you're speeding up on the highway, that's what we call an acceleration. We'll write this as A average. This is the average acceleration. Again, we'll just jump right to the end. What if we want the acceleration over a very, very tiny time interval? We want the instantaneous acceleration. Well, A, without the average, we will define as the limit as delta t goes to 0 of the average acceleration. That will be the limit as delta t goes to 0 of v minus v naught over t minus t naught. And that's what we will call the instantaneous acceleration. Typically, we usually think of an acceleration when something is speeding up, and when something is slowing down, we call that a deceleration. However, in physics, we're not going to use the term deceleration. We'll talk about a positive acceleration. Say if something is moving to the right and speeding up, we'll call that a positive acceleration. If something is moving to the right and slowing down, that's still an acceleration, but we'll just call that a negative acceleration. So we can have positive and negative accelerations. Because acceleration is a vector, it can point in any direction. And rather than saying one is positive and one is negative, and we'll call the positive acceleration, the negative decelerations, no. They're all going to be accelerations, but the vectors can point in different directions. Okay. Oh, before I erase this, what are the units going to be for acceleration? Now, typically, whenever I want to talk about the units of a quantity, I will put that quantity in square brackets. So, let's say R. What are the units of position? The units of position we've already seen are meters. What are the units of velocity? Units of velocity are meters per second. What are the units of acceleration? Well, the units of acceleration will be the units of velocity divided by the units of time. Units of velocity are meters per second. Units of time are seconds. Meters per second divided by seconds. Those will be meters per second squared. So the SI unit for acceleration will be meters per second squared. Okay, so let's look at a couple more overheads. Here we go. So here we have an object initially going here with some initial velocity, let's say 30 meters per second, at an initial time of t equals 0. Later on, moving at 10 meters per second with a final time of 2 seconds. Let's see if we can figure out what the acceleration is. Acceleration is final velocity minus initial, so 10 minus 30 is negative 20. Time interval, 2 minus 0, 2 seconds. So negative 20 meters per second divided by 2 seconds, negative 2 meters per second squared. So the acceleration in this case is negative 20 divided by 2 is 10. Negative 20 meters per second divided by 2 is negative 10. So we have an acceleration of negative 10 meters per second squared. Let's make sure I get that right. 10 minus 30 is negative 20. Negative 20 divided by 2 is negative 10. There we go. Negative 10 meters per second squared. So we have a negative acceleration, which is telling us basically that the car is slowing down. It's going from 30 meters per second to 10 meters per second. Negative acceleration means the car is slowing down. Okay, let's take a look at this one. Got a number of pictures here. All right, so here's a car with a velocity vector shown above. And what we notice is the velocity vector looks uniform. What is the acceleration in this case? Well, we pick some velocity over here minus an initial velocity. They're the same velocity, so the difference is going to be 0. The acceleration is 0. 0 acceleration means constant velocity. So we have a 0 acceleration in this case. Let's look at another one here. In this case, we have a small velocity that is increasing to the right. If we take one velocity over here, subtract one of these over here, we end up with a vector still pointing to the right, divide by the time interval. So what does this mean? We have an acceleration pointing to the right. This is a positive acceleration. In other words, an acceleration pointing in the same direction as the car. So what do we have? We have an acceleration. The acceleration vectors are then shown below. The accelerations are all to the right. Let's look at another one. Whoops, here. What do we have? We have a large velocity that is then decreasing. We take a vector over here, subtract one over here, we end up with a vector that's pointing to the left. Divided by, let's get something flying around in here. We end up with a vector pointing to the left, divided by the time interval. What do we end up with? We end up with an acceleration vector pointing to the left. So notice, positive acceleration here, or to the right, in the same direction as the velocity, basically means the car is speeding up. Acceleration vector pointing in an opposite direction to the velocity basically means the velocity is decreasing. The car is slowing down. Let's look at the exact reverse situation. Let's look at the one up at the top. We now have the car moving to the left with a uniform velocity. Subtract any one of these from another, you get 0. Still, 0 acceleration. Even though it's moving to the left, the velocity is uniform, 0 acceleration. Let's look at the car. This mosquito is trying to get me. Not anymore. Here is the car moving to the left, but now it is speeding up. We take a final velocity here, subtract an initial velocity here. We end up with a vector pointing to the left. What do we have? We have an acceleration vector pointing to the left. So the car is speeding up, but we have a negative acceleration, a vector pointing to the left. This acceleration is pointing in the same direction as the velocity. That means the velocity is increasing, or the car is, I should say, the car is speeding up. Acceleration in the same direction as the velocity, the car is speeding up. What do we have in this case? In this case, the velocity is decreasing. The car is slowing down. Take this vector, subtract this vector, you end up with a velocity vector, a change in the velocity that points to the right. So this is an acceleration to the right. In this case, although the car is moving to the left, it is slowing down. And so the acceleration points in the opposite direction. This is a positive acceleration. This is why we don't use the terms acceleration and deceleration. Here is a speed that is decreasing. The car is actually slowing down, but that is a positive acceleration. So rather than saying something like that, to make it confusing, here is a velocity vector pointing to the left. It is slowing down, but this is then an acceleration pointing to the right. In terms of the component, this would be a positive acceleration, a positive x component of the acceleration. Okay. Sometimes some problems give rise to numbers that aren't very pretty, but here's a jet that is taking off, starting off at 0 meters per second at 0 seconds. Actually, they've changed units on us. 0 kilometers per hour, 9 kilometers per hour, 18 kilometers per hour after 2 seconds. Change in velocity, 18 minus 0 is 18 kilometers per hour. Delta t is 2 seconds. The acceleration is then 18 kilometers per hour divided by 2 seconds. So here they've actually given the average acceleration as 9 kilometers per hour per second. Not exactly nice units, but the important thing is, notice we have a distance per time per time. So those would be appropriate units for acceleration, just not standard SI units. Let's take a look at one more. Here we go. Here is a car slowing down because of the influence of a parachute. What do we have? Initially at t equals 0, it's going at 28 meters per second. 1 second later, it's going at 23 meters per second. After 2 seconds, it's going at 18 meters per second. What's the acceleration? Well, 18 minus 28, that's negative 10. Over 2 seconds, negative 10 divided by 2 is negative 5. We end up with an acceleration of negative 5 meters per second squared. Negative because the acceleration is in the opposite direction of the velocity. In other words, because the velocity, the magnitude of the velocity is decreasing, the acceleration is in the negative direction, or the opposite direction compared to the velocity. Okay. Just a couple more important ideas. All right. Can we have a positive velocity and a positive acceleration at the same time? Well, yeah, so that would be something like positive velocity is motion to the left, positive acceleration means it's speeding up, so motion to the left, speeding up, that would be positive velocity, positive acceleration. Can the velocity be positive and the acceleration negative? Yeah, so here we've got an object moving to the right, negative acceleration in the opposite direction to the velocity, that means it's slowing down. So we've got something moving fast and then slowing down. So that would be positive velocity, negative acceleration. Can we have negative velocity, positive acceleration? So here we've got something moving to the left. Positive acceleration means acceleration in the opposite direction to the velocity, so that must mean the magnitude of the velocity is slowing down. So in this case, we've got something moving to the left and slowing down. So that would be positive velocity, negative velocity, positive acceleration. Can we have negative velocity, negative acceleration? Go ahead. So can we have a velocity that's less than 0 and an acceleration that is less than 0? So a velocity less than 0, that means motion to the left. Acceleration that is got the same sign as the velocity means the velocity is increasing. So here we've got something where we've got motion to the left, starting out slow and then speeding up. So negative acceleration, negative velocity, negative acceleration. Now, what about, can we have some velocity, and it doesn't really matter which, let's say positive velocity, and an acceleration that is 0? Well, yeah, what does this mean? Positive velocity, that means motion to the right. Acceleration is 0, that means no change in the velocity. So we've just got constant motion. Motion moving at a constant rate to the right, not changing the speed, 0 acceleration. Can we have a 0 velocity and an acceleration that is not 0? Can we have a 0 velocity with a non-zero acceleration? Well, oddly enough, yes we can, but only instantaneously. So if we think about, say, a motion like this, let's imagine we've got something that is going up in the air and then coming back down. So when it's going up, the velocity is upwards, we might say positive. And when it's coming down, the velocity is downward, or we might say negative. Now, what is it right at the top of the motion? It goes from being positive to being negative. Right at that peak of the motion, the velocity is actually 0, instantaneously. Because the velocity is changing, it's slowing down on its way up and then speeding up on the way down, we have a non-zero acceleration. But just at the peak of that motion, we do have 0 velocity, and so that is possible. And we'll come back to this and talk about this more later on when we actually start dealing with things falling under the influence of gravity. All right, one last thing. Let's take a look at just a few more graphs of motion. We're going to talk more about these next time. Let's think about what these motions actually look like. We'll look at some graphs and then talk about what they mean. Let's imagine we've got a velocity. Here we've got a velocity as a function of time. Let's imagine we've got something where the line is right along the t-axis. What does that look like? Well, we've got 0 velocity for all time. Basically, we've got something that's not moving. It's stationary, is pen, stationary, not moving, velocity is 0, stays 0 no matter what time it is. Okay. What if we have something, a horizontal line, but that is not along the t-axis? What would this motion look like? So here we've got a velocity that looks like this. In this case, we've got uniform velocity, a constant velocity, but it's non-zero. So here we've got an object moving along at a constant rate, not accelerating, constant uniform velocity. If it was down here, that would be a negative velocity, moving to the left. Okay? What does the motion look like if we've got something like oops, sorry, not T. Like that. What is that motion going to look like? In that case, we've got some velocity that is changing as a function of time. So right here, we've got something with some velocity that is then going up as time increases. So we've got something that's speeding up. It's maybe moving slowly and then going faster and faster and faster and faster. What if we have something like this? It's supposed to be horizontal there. We've got something, let's say, initially stationary, starts moving in the positive direction, and this is V. Start moving in the positive direction, speeding up, speeding up, speeding up, comes to a point, moves at a constant velocity for a while, and then slows down and eventually comes to rest. So we've got something speeding up, moving at a constant rate, slowing down, and coming to rest. Okay? All right. So we'll come back to these ideas more later on and talk about, again, the relationships of velocity, position, and acceleration more next time, and then we'll look into multiple dimensions, motion in 2 dimensions.